Hello and welcome to our next set of college algebra notes. We're on Unit 2, Outcome 3. So we're 3 sections into our second unit. We talked about solving quadratics in our previous section. This section we're going to talk about how to graph these quadratic equations. Remember, it's a quadratic equation because it has an x squared in it. That's what makes it special, makes it a quadratic equation. We'll deal with equations with higher powers later, but right now we're dealing with things that just go up to the x to the second. Every graph of a quadratic, every single time you graph a quadratic, you're going to get this basic shape. It's going to be what we call a parabola. So that's just the fancy name for this. This is called a parabola. It's a curve. Parabolas can open up or they can open down. So this one I'd say opens up because you have the two arrows going upwards forever and kind of the bottom point here. You can have this flipped over. So you got a parabola that looks, like that, upside down. It cannot open side to side. That would not work. If you turn parabola on its side, notice that it fails the vertical line test. So it wouldn't be a function. So parabolas only open up or down because parabolas are functions. This is a parabola. Notice that parabolas typically have some x-intercepts. A lot of times they have 2 because of this curve. It is possible for them to just have a repeated 1. That's when the low point here is on this x-axis. So sometimes some parabolas, some weird ones, will have just 1 point for their x-intercepts, but most of them have 2. That's kind of the typical. They will always have a y-intercept. There's always going to be some point where they cross the y-axis because they do go out left and right forever. Now, these arrows are pretty steep, but they're going to be going out to the right forever and they go out to the left forever. So they'll always reach left and right forever, so always at some point it's going to cross the y-axis, the y-intercept. Parabolas also have this line of symmetry. It's right in the middle here. You can see there's this vertical line. And you can see that you could fold over this line and the two halves match. You notice that this does not need to be centered, so it's not right in the middle. A lot of parabolas are centered, so you will see some that have the y-axis as their line of symmetry, but a lot of them aren't too. So yeah, that's something to pay attention. They always have this line of symmetry. Always a vertical line that you can fold it over. And very important, the vertex. The vertex of a parabola is the turnaround point. It's the point where it stops going down and starts going up, or vice versa. It stops going up and it goes, turns around and goes the other way. So like here, it's going down until it's that point and it goes back up. But if you have one that goes upside down, it stops going up and then it comes back down. So it's your turnaround point. Your vertex is either going to be the lowest point if it opens up like this, or if it opened down, that would be the highest point. So it's always going to be kind of a minimum or a maximum for your quadratic equation. The vertex, we like to label it with a coordinate we call HK. And when we write the nice standard form of a quadratic, we use that HK in the standard form. So H is going to be the x value of your vertex, and K is the y value of the vertex. And so parabolas in standard form. So this is kind of the nice way to have a parabola's equation. Is written where we have a times parentheses x minus h, which is the h from the vertex, that quantity squared, plus k, which is the k from the vertex. You'll notice that we have a square here that's going to square this x, so this does have an x squared in it. But we've kind of factored a little bit into something squared. So that's why we have it in this form. This a in front here, what this is actually going to do is a is actually going to tell us whether this parabola opens up or down. So this a here in the front actually tells you whether it's probably opens up or opens down. If a is positive, if it's bigger than 0 or positive, then this parabola will open up and it will look like this shape. That would be a parabola that opens up, then it opens up. So it would look like this. If a is less than 0, well, you can think of this like when we did the graph transformations. If we have a negative number in the front, remember that a negative on the outside flips it vertically. So if this a is a negative, if there's a minus in front of it, it takes the parabola and flips it upside down. And so if a is less than 0, it opens down. It looks like this. And that's what's happening. Basically, if there's a negative in the front here, then the parabola got flipped over, and it's going to be looking like this instead, because it's flipped upside down. So that's why sometimes they open up, sometimes they open down. All is determined by whether they have a positive or negative in the front, because that sign can just flip the whole thing over. Okay, so first off, if I give you a parabola in this nice standard form. It's great to have standard form. Standard form is really handy. If you have it, you can just look at the equation and you can tell me where the vertex is, and you can tell me whether it opens up or down just by looking at the equation. You don't have to do really any math. So in this case, we'll look at the equation, and it says find the vertex. So we're going to find that vertex. We're going to determine if it opens up or down. And we're also going to think about whether it's stretched or shrunk. Now remember, when you multiply by a number, you stretch it or shrink it. So this number in front here can determine actually if it's stretched out or shrunk. Remember that since it's on the outside, with graph transformations, we say stuff on the outside, if it's bigger than 1, it stretches, and if it's smaller than 1, it shrinks. Maybe I should just make a note right here, over here real quick, that if A is bigger than 1, it's a stretch, but if A is less than 1, it's a shrink. Now remember, we're always working with the positive version. We're kind of ignoring the sign when we think about stretch, shrink, and this is always a vertical stretch, shrink, because it's on the outside. It's not inside the parentheses. Okay, so we're going to look at all three of those things. So if I look at this parabola, I can see that it's got the -3, the +2, but the minus is built in there, right? So that we're actually not going to worry about the minus, we're just worried about the number. So we're going to worry about the 3 here. So the h part of the vertex is going to be 3, because that's the h part, this is h. And then the k part is this k on the outside, and there's a plus here, so we just leave that plus like it is, and so we just take the 2. So hk, that's hk from right there. So first off, we can tell, yep, this is the vertex, the point 3, 2. So if I graph this, I would go over 3, up 2, and that's where its vertex would be. If it opens up or down, well, in this case, a is 2, which is bigger than 0, so it's positive, right? It's a positive number, so it opens up. So this opens up because this a value is bigger than 0. Last thing, a is 2, which is bigger than 1, right? That's more than 1, so it's a vertical stretch. So again, if it's bigger than 1, it's a vertically stretched graph. So what that means for a parabola is if you vertically stretch it, it's just going to end up looking skinnier, because the point that would be here, instead of being here, is going to be stretched vertically, stretch it out. So it's going to be down here, and so it's going to have a middle point here, and it's going to more steeply kind of come up. It's still going to hit 3 here, but it's going to be going up faster. It's going to be coming in faster because it's stretched out. It's like taking this like a piece of elastic. You take a rubber band and you stretch it out. It looks skinnier. Okay, so we can tell all that information just from looking at the equation. That's the wonderful thing about this standard form. If you have standard form, you can just see the vertex. There's the 3, there's the 2, that's the vertex. The A in front, again, it tells you which way it opens, so we know which way this one opens, and it tells you it's vertically stretched or not, or shrunk. And so this one's vertically stretched because, of course, 2 is bigger than 1. Let's try one more like this. Okay, so again, the first thing we have to think about is the vertex. Vertex always comes from the number inside. This is going to be your h, so this is my h, and the number on the outside is the k. H, this time you notice I have a +5 instead of a -5. Well, the reason you get a +5 like that is because you actually have a negative. That's, remember, a double negative makes a positive. That means this 5 here is actually a -5. Because the reason this minus turned into a plus is we put a -5 in for h. So we subtract a negative. Well, you always subtract a negative into plus, and that's why it's -5. So notice that the sign here for the h, is always going to be opposite of the sign of this sign here. So if we had a 3 instead of a -3, -5 instead of +5. And that's always going to be true for the h part because of that built-in negative. The k part is going to be this 3. So 3 is the k, and that's our vertex. So because of this 5, we got a -5, 3 got 3, that is the vertex. So left 5, up 3, and that'd be where this vertex goes. Next thing we want to see is a bigger than 0. Well, a is -1 in this case, right? Because we have this sign here. This is going to be our a. And remember, there's always a default 1 in front of parentheses. So you can think of this as -1. So a is -1, which is actually less than 0. So this one would open down. So it would go downwards and be upside down. Again, that's just because the sign here is negative. I flipped it over. Last thing, a is 1, right? So here we're ignoring the negative. We're just looking at the 1. And a is 1, which is not bigger than 1, and it's not less than 1. It's not bigger than 1, and it's not less than 1. So it's not stretched or shrunk. Since a is exactly 1, again, we're ignoring the negative when we do the stretch shrunk. We're just looking at the number, not the sign. If it's exactly 1, then it's not multiplying to make it bigger or dividing to make it smaller. It's just exactly 1, so it's just staying the same. So it's going to look like this one does. It's just going to be the same curve. It's not going to be stretched or shrunk because a is 1. All right, so that's the standard form. A standard form is on your formula sheet, so the standard form will be given to you. But again, you need to know how to pull the a, the h, and the k out of there. If I use hk to get your vertex, and from a, you should be able to get this kind of information. You should know about whether it's stretched or not. You should know about whether it's opening up or down. But that's really kind of coming back to our graph transformations. So if you remember your graph transformations, that's actually pretty straightforward for this, because a is just the number in front. The negative, it's flipping. If it's bigger than 1, it's stretching. If it's smaller than 1, it's shrinking. Okay, so let's take a function in that standard form, and let's graph it now. Let's actually see what it would look like to graph this. The first thing you're going to do to graph this is you are going to look at the vertex, because knowing where the vertex is a really important part of graphing a quadratic function. So I'm going to look at the h, I'm going to look at the k, and again, remember that the standard form is a parentheses x minus h squared plus k. That's our standard form. That's what the function should look like with the generic a, h, and k. So h, the minus there is built in, so we just get the 1. So the vertex, the first part is just the 1. K is just the same 4. Again, the plus is what it should be, and that's our vertex. So first off, when I graph this, I go over 1, up 4, and that is the vertex. Now when I graph these, I notice that the vertex is up here, and I think about, if this opened up, it wouldn't even cross the x-axis. If it opens down, it will cross the vertex. And that's one reason why it's so important to know if it opens up or down. Because when you know which way it opens, you know whether or not you're going to actually cross this x-axis. So looking at this, I say, okay, which way is it going to open? Well, a in this case is negative 1 again, right? There's a negative there, so it's negative 1, which again is less than 0. It's negative, so this is going to open down. So that means actually, yes, it will cross the x-axis. So there are going to be x-intercepts. There are some quadratic functions that don't have x-intercepts because they'll open the wrong direction. It'll open up here, it'll be down here, and open down. And then they won't have any x-intercepts. Sometimes you'll look for an x-intercept and you won't find one, and that's when you look for an x-intercept on a graph that doesn't cross it. So this would be an example that does have one, but if it opened up, if we put a positive in the front here, it would never have any x-intercepts. It would be pointless to look for. Okay, before I get to domain, range, and all that stuff, let's talk about those x-intercepts. Let's find those. How do I find x-intercepts? Well, remember, you find x-intercepts by setting the y equal to 0. We talked about this earlier in the semester. We said the intercepts, remember, are where you cross the axes, and to cross the x-axis, your height has to be 0, which means the y value has to be 0. So we always find x-intercepts by setting y equal to 0. Well, what's y in this equation? Remember that y is the same thing as f of x. So we're actually just going to set this equation equal to 0, because f of x is just another way to write y. This just tells us the function. So we have 0 equals negative parentheses x minus 1 squared plus 4. So we're going to solve this equation. Now to solve this, there's a couple different methods and stuff, but I think the easiest thing to do is to actually get this squared part by itself and just use the square root property. Remember that if you have something squared, if the x part is just inside the square, you can square root to get rid of it. Now I'm actually going to move this one across, not the 4, because I don't like having this be negative. So I'm going to add the x minus 1 squared to both sides. So by adding it to both sides, I can cancel the amount on this side. That's gone because opposites cancel. And I just get x minus 1 squared equals positive 4. And now I can square root both sides. So that's the idea. You like to do this so that we can square root both sides. Don't forget when you square root both sides, the number side, you always get that plus or minus. The idea is that if you have something squared and you square root it, the square and the square root cancel because they're opposites, right? Squares and square roots are opposites. So this just becomes x minus 1. Power and the root canceled. Over here, we know that we can square root 4, we get 2. So this becomes plus or minus 2. Square root of 4 is 2. And then the last thing, we're going to get x by itself. We're going to add 1 to both sides. Get rid of this minus 1. So we're going to get rid of this thing. And we get x equals 1 plus or minus 2. Well, we can solve that, right? We do 1 plus 2 is 3. 1 minus 2 is negative 1. And those would be the x-intercepts. So the x-intercepts is going to be 3 and negative 1. That means if I graph this, then it can cross at 3, that's going to be one of them, and at negative 1. And when you do this, one thing you should look for is you should look for the symmetry, right? We said that there's symmetry, and the rule is the symmetry always goes through the vertex. So that's actually where our line of symmetry is. It's actually right here. This is the line of symmetry. And remember, since it's a vertical line, if you want to write the equation of this line, you write it by doing x equals, and then whatever number it hits. Well, this is at 1, so it would be x equals 1. So the line of symmetry, or the axis of symmetry, would be x equals 1. They usually want a line, because it is a vertical line, and to make a vertical line, we always use the equation x equals whatever number it goes through. Notice that the number it goes through, the 1, is the coordinate of the vertex, the x coordinate of the vertex, because it's always going to hit the vertex. So you can do that. As soon as you know what the vertex is, you kind of know what the line of symmetry is. It's always going to be x equals whatever the x value of the vertex is, because it always goes to the vertex. Now, why do I talk about the line of symmetry? Well, because if you know what the line of symmetry, that because it's symmetric, these 2 points should be equally distant from the line of symmetry. So you can see this distance is 2, that distance is 2, and that's showing me that I'm doing things right. You know, if you get these 2 points and they're not symmetrical about this line of symmetry, that tells you that maybe you messed up solving to find your x-intercepts. Now, you can graph this with just the x-intercepts. So if that's all you need to do is just graph it, you can find these x-intercepts and you can just draw the graph and you're good to go. You can't just graph it with a vertex because you need to know how wide to make it. So having the intercepts here is kind of the way to make it wide. On my lab, when you're doing the homework, you'll actually get a tool where it'll just have you graph a parabola. It's a parabola graphing tool. And it'll have you pick 2 points. So it usually works good enough just to pick the vertex is 1 point, because that's usually pretty easy to find. And then one of the intercepts is the other point. So you have this one or that one. I think it's pretty nice. It only makes you use 2 points. So if you have those 2 points, you're good enough. You don't even have to have both vertex. In fact, you don't even have to find the x-intercepts because you could use the y-intercept. So let's do one more point. Let's do the y-intercept. Now to find the y-intercept, kind of like the x-intercept, we set a value equals 0, but with the y-intercept, we set x equal to 0. Remember that if you're a y-axis intercept, if you're on the y-axis, that means that your horizontal distance is 0. You're in the middle horizontally. That's why your x value is 0. So the y-intercept, x is 0. So if we set x equals 0, we're going to put 0 in for x in this equation. So basically we're finding f of 0, plugging 0 in for x. That will give us the y-intercept. So we get negative 0 minus 1 squared plus 4. And this one, it's not something you even have to solve. You just have to, simplify it, just run the math. And so we do the order of operations, do subtraction first. So I get negative 1 squared, still minus, still plus 4. We know that we square a negative, you get a positive, so this becomes positive 1. So we have a negative, positive 1, so that just makes a minus 1. Still plus 4. And negative 1 plus 4 gives me 3. So the y-intercept is 3. So actually, I can just use this point 3, which is my y-intercept, and the vertex, and that would be enough to graph it as well. So if you're in my lab, you can just use those 2 points. And you might notice that that was actually a little bit easier, right? It was a little bit easier to find this y-intercept than the x-intercept, and that's usually true. So if you come to a quiz or a test question and you're just trying to graph and you need an intercept, usually finding the y-intercept is probably going to be the easier one. I recommend in the homework you try to do both, because this is good practice solving quadratics, which is something you have to do on this test coming up, because that's what we did in the last section. And I also can ask for both on the test, right? We have a written part, so it's possible I might ask you for to find the x-intercepts of a quadratic. So it's a good idea to be ready to do that if needed. But it's also good practice solving quadratics. Okay, so now we have enough on here. We can definitely graph this. I'm going to go ahead and draw the lines. Again, my lab will do this for you when you're doing the homework. But I have to do it by hand. So it's not pretty, but that's what it would look like. It opens down, like we said. It has its vertex at 1, 4. It's got its y-intercept, its x-intercept. It's got the axis, symmetry at 1. Last thing to do is talk about the domain and range. Remember, the domain and range of a function, domain is always the x's. So it's always how far left and right it reaches, how far to the left does it go, how far to the right does it go. When you look at this graph, you notice it's going to the left here. It's actually continually going to the left. It can never go straight up and down, because then it wouldn't be a function. So it has to keep going to the left, just kind of going really far down as it goes to the left. This one goes to the right, just goes really far down as it goes to the right. But that's what it looks like. So the domain for this one is actually negative infinity to infinity, because it goes forever to the left and forever to the right. In fact, that's true for all parabolas, because parabolas always have this shape where they open outwards. They might open up, they might open down, But either way, they're going to open outwards both ways. And so it's always going to have domain negative infinity for all parabolas. That's a rule. So as soon as you see you're working with parabola, you know it's going left and right forever, so that you know that's the domain. Now the range is a little different. Range, remember, is the y's. How far up and down is it going? And parabolas do stop, right? They hit the vertex and they turn around and go the other way. So parabolas will always have a part of the range where they'll stop. So like this parabola stops at 4. So its ranges go up to 4. That's going to be the top number. And it stops. Because it actually reaches 4, that's its vertex. We'll use a bracket because it reaches it. When we go down, we notice it goes down forever. It's just going down, 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 down. So it does go down to negative infinity. And that would be its range. And there you go. That's the interval notation. It's coming back again. And I'll just say now, those of you that didn't like on the test, they have people said they didn't like on the test, this interval notation is here to stay. We're going to use it all semester because we're going to be dealing with domain and range of all kinds of functions. And so we'll be using this all the time. Primarily for domain and range. That's probably the number one reason we'll use it. So that's what I think the primary usage we'll have for it. But yeah, the interval notation, you've got to get comfortable with it because it's something we're going to see a lot of. Again, always start with the smallest number and go to the biggest number. So I start with negative infinity because it's the smallest I can get. And then it goes up to 4 because 4 is the biggest it can get. Use brackets when you're including the value. If we reach 4, we had to use a bracket. Again, you can't reach infinity, so we use parentheses. So that would be the domain and the range. So you go from this equation, not too hard to get this parabola, because again, you just need to find the vertex and then one of these intercepts. I did all three, so I actually did more work than I needed to. Either one of these would have been enough to give me the rest of the parabola. So again, you could just done this process and gotten that 3, and then those 2 points would be enough to draw the whole parabola, because you kind of know what this looks like. You might be thinking, well, how do I get this arm if I only had this piece? Like if I didn't do the intercepts? How would I get this side? Remember, there's the symmetry, right? So there's just like this one's 1 across, this one should be 1 across. So there's going to be a point there by that symmetry. So that's how you could get both sides if you do it by hand. Again, MyLab will kind of do it for you, so that makes it easy. Okay, now I did all this so far with the nice standard form, but the standard form doesn't always happen. We've seen lots of quadratics already that weren't written like this. So the rest of this section, we're going to talk about quadratics that are not in standard form. So what if your quadratic looks like this? You know, it's just that typical ax squared plus bx plus c, something like this. Then what do? Well, there's a couple ways to do it. One way to deal with this is you can actually write it in standard form. And if you really like completing the square, you can use that method. I think your book might actually show you that and help me solve this or that. It's not the easiest way to do it, though. So there's a little bit easier way to deal with this besides using, you know, the completing the square. So I'm not going to really worry about trying to show that. If you do end up in a situation where you need it, you can look it up, how to do completing the square with a parabola. But I'm going to do it with a little trick, a little equation, actually. And so the equation we're actually going to use is this equation right here. This equation says that you can find the h value. Remember the vertex is the coordinate hk. It says that you can find the h value of the vertex by just taking negative b over 2a. Remember that a, b, and c, that the b is the number in the middle, and a is the number at the front. So I can just use b and a, and I can find the vertex. I don't have to do anything more than that. So actually, I'll use this all the time to get my vertex. This will give me the first half, and then we'll talk about how to get the second half. So first off, I want to find the vertex for this thing. First thing I'm going to do negative b over 2a. So negative b would be negative 12, right? Because we call this whole thing b. Would be negative 12. So we put negative, because there's a negative in front of the b, and then we put the negative 12, negative 12, over 2 times a. So I'm going to put 2, and then a, of course, is going to be 3, because it's that number in front of the x squared. The first number is a. So put times 3 on the bottom. So this, once I simplify it, will give me the h value. That'll give me the first part of my vertex. So I do negative 12. Well, double negative we know is a positive, so that's positive 12. 2 times 3 is 6, and 12 divided by 6 is 2. So this is h. That's the first part of the vertex. So my vertex is going to have the first part is going to be a 2. Now that's only half the vertex. I'm not done yet. I need to find the second half, the second part of this. Well, how do I find the other part? Well, this is a function, right? This is a quadratic function. It's got a function label right here. It's a function, and we know x. So we can always use a function to get the output, y, by just plugging in the input, x. That's what this is telling us right here, that if you want to find k, the second part, just plug in h. Remember this notation, f of h means plug in h and see what you get. So we're going to plug in this 2 we just got, and that will give us k. So k is going to be f of 2. And whatever we get, we plug 2 in. So here we're going to plug 2 in for all these x's here. So we get 3 times 2 squared minus 12 times 2 plus 1. Here we have 2 squared. 2 squared gives 4. Remember, you always do powers before you multiply. That's a pretty common mistake, is people try and multiply here first and then do a power. But we know that PEM does, the order of operations tells us you do exponents before you multiply. So 2 squared gives us 4, so we get 3 times 4. Here I can do 12 times 2 because you multiply before you subtract or add, so I get 24, so minus 24, still plus 1. 3 times 4 is 12, so we get 12 minus 24 plus 1. If I do 12 minus 24, I get negative 12. Add 1 more, you get negative 11. So that's the output. So that is the y value, or k. So we take the x value we got, and we take the value for h, and we plug it in to get the value for k. That's the idea. So plug in 2 to get k. That's what we're going to do. The 2 that we got that was h, that's h. That's what we plugged in, and that's how we got k. And that's the trick here. So you can see how this would be a lot easier than like completing the square. I don't know about you, but I think this is much easier if you know this formula. And again, in real life, if you're out and about in the workforce stuff, you can just Google the vertex or parabola formula. On the test, you'll have this formula on your formula sheet. So it's pretty easy to look up. A small little easy formula. So we'll just use this to find the first coordinate. So use that to get your h, and then plug that in to get k. So that's our vertex. One little side note about this, something else that we noticed. So with the other standard form, we were able to tell whether it opened up or down and if it stretched or shrunk. Well, we can actually still do that because the same a we had before is this same a we have now. So a is still 3. It's still the first thing in the front. Just like when we had the, parabolas in the standard form, you can look at the number that's in the very front. In the non-standard form, you can look at that a, it's the very front number, and it tells us the same information. So first off, because that is bigger than 0, this is going to open up. Because it's bigger than 0, it's going to look like that. So because there's no negative in the front, we know this is going to open up. Also, a is 3 is bigger than 1. It's a big number. We know that this is vertically stretched. Again, if it's bigger than 1, we know that's going to be stretched. If it was smaller than 1, it'd be shrunk, and if it was 1, it'd just not be stretched or shrunk. But you can tell all that from here. So even though it's not in standard form, it's actually still really useful as long as you know this little trick to find the vertex. Once you got the vertex, again, you can still figure out all this stuff, and then we can go graph it, which we'll do on the next page, so I'm not going to worry about it here. Okay. I'm going to do one question before I get to graphing. This question actually asks us to find the minimum maximum of this function before we even graph it. So we're not going to graph it to find it, we're going to do that. Now, the trick with this is the fact that the vertex is always a minimum or a maximum, right? The vertex is the turnaround point, so it's either the bottom where it turned around and came back up, or it's the top where it turned around and came back down. So this is always going to be the vertex is what they're actually asking for. And they give us this function, ask for the vertex. We'll notice in this case that the a value, again, is actually 3. You pick the same number twice in a row. Whoops. Oh well. This is 3. And since 3 is bigger than 0, this one also opens up, just like the last one. Not a big surprise, it's the same number. Okay, so that opens up, which means it looks like this. Well, if it looks like this, the vertex is down here. We know that the vertex right off the bat has to be a minimum. So I'm not even looking for a maximum because there is no maximum to this graph. Right? It goes up forever, but it has a minimum. So that's why they asked for either one. Well, in this case, they want the minimum. So just by using a, we know we're looking for a minimum, and we know that the minimum will be the vertex. So now to find the vertex, we're going to go back to that little negative b over 2a formula. That's our important formula we use for finding the vertex. So we use h equals negative b over 2a. We know a is 3. We can see here that b is negative 18. And so we're going to use those in this equation. We'll find out what the vertex, the first part is. So again, negative, and b is going to be negative 18, so negative 18, double negative again. And 2 times a, which we said is 3. Well, negative 18 makes a positive 18. 2 times 3 makes 6. And the answer ends up being 3. That's the first part of the vertex. The vertex is going to be the point 3 and then something else. Now to find the second part of the vertex, again, we're going to do what we did before. We're going to plug in 3. So I'm going to do this, sorry, this is the h function now. So I'll do h of 3. H function, h of 3. equals 3 times 3 squared minus 18 times 3 minus 3. Lots of 3's in this problem. I wrote a lot of 3's in here. Okay, 3 squared is 9 times 3 is 27. Right, square first and then multiply. So 3 squared is 9 times 3 is 27. 3 times 18, what is that? 30 plus 24? I think that's 54. That's a big number. Okay, minus 3. 27 minus 54 is going to be 27, actually. And then minus 3 more is going to be 24. So I think that gives us 24 if I did my math in my head right. So my vertex is going to happen at 3, 24. Now, when you're answering questions about maximums and minimums, there's a couple different things they can ask for. One thing they could say is, what is the minimum? Well, for this problem, the minimum is actually 24. That's the smallest it gets, right? That's the low point. Oh, I forgot. That's a negative 24. Whoops, I forgot the sign. I wondered why our minimum was so high. And it could be positive 24. That's possible, but this was supposed to be negative because 27 minus 54 is negative 24. Or 27, sorry, minus 3 more. I did it wrong. I made a mistake. Well, that's why we go back and look at our work, right? Yeah, let's do it with the calculator so we can see what I should have gotten. 27 minus 54, and then we minus 3, and I should have gotten negative 30. So I really messed that up. Sorry about that. Negative 30, much better. There we go. So this is negative 30. And this is negative 30 is our minimum. So that's what our minimum should be. Our minimum should be negative 30 on this. That is the minimum, that's the lowest value it can get because it opens up and that's the lowest it's going to get. Sometimes, though, instead of asking what the minimum is, they may ask, where is the minimum at? Where is it located? A lot of times in that terminology, they're actually looking for the value 3 because they're asking how far left and right it is, and that's your x value. Or sometimes they'll ask for the minimum's point. You know, what point is the minimum? And then they're looking for this pair. They're looking for the 3, negative 30, the actual vertex pair. So just watch what they're asking for. If they're asking for the pair like this, the point, usually on the little subtext underneath the question, they'll say answer is an ordered pair. So then you're looking for this. That's kind of a hint for that one. Otherwise, they'll just ask for a number for these two. But just be careful. Are they looking for the minimum, or are they looking for where the minimum happens? And those are slightly different questions. You know, again, the lowest number is negative 30, but it happens at 3. Okay, last thing. From this, we can actually talk about the domain and the range. So we don't even need anything else. We can just look at the domain and the range from what we found here. First off, domain is really easy because remember, domain is the x's. That's how far left and right. And I said parabolas always up and upwards, so they always go out left and right forever. So this is always negative infinity to infinity. So that one's pretty easy. As long as you're talking about a parabola, as soon as you have a quadratic like this, domain is in negative infinity to infinity. The range, however, this is where I have to stop and think about the fact that it opens up, so it's got a bottom. And we saw that the bottom is negative 30. After I fixed that, we figured out the negative 30. It does reach the vertex, so we use a bracket. You're always going to have brackets with these parabolas because they'll hit their vertex. And then it goes up forever, so it's going to go to positive infinity on the top. And that would be the range. Again, the range is the y's, the domain is the x's. These are the numbers you reach left and right. These are the numbers you reach up and down. Okay, now I want to graph, and this is our last page. We're almost done. It's a short section. I want to graph a parabola that we're given in this non-standard form. So again, to graph these, it's nice to know the vertex. It's nice to know some intercepts. That's what we use to graph these. So first thing we do, I'm going to find the vertex. So what is the vertex for this? Now remember, to find the vertex, we're going to use that formula that the h value of the vertex is equal to negative b over 2a. Here, a is going to be 2, because it's the number for the x squared. B is going to be 4. I don't really need c, but I'll just say c is negative 2 just for practice. But yeah, this is all I need, b and the 2a. So b is 4, so I end up with negative 4 on the top. Here there's no negative here, so that's why this ends up just being a plain negative 4. On the bottom I have 2 times a, which is 2, so 2 times 2. I end up with negative 4 over 4, right, because 2 times 2 is 4, and that gives me negative 1. So the first coordinate is negative 1. That's the first part of the vertex. Remember, to find the second part, we just plug that negative 1 we got into the function. So we do f of negative 1. We get 2 times negative 1 squared plus 4 times negative 1 minus 2. Well, here, negative 1 squared becomes a positive 1, right? Negative times negative is a positive. 1 times 1 is 1. And then 1 times 2 gives us 2. So we get 2. 4 times negative 1 is a minus 4. And then minus 2. Well, 2 minus 2, those are 0, so we just end up with negative 4 for that. So the second part is minus 4. And that's our vertex. So our vertex is at negative 1, negative 4. It's down here. That's where the vertex is. Now again, when you're doing this, it's good to know whether or not you have x-intercepts. And we're only going to have x-intercepts if this opens up. So if you look at A, if you look at A, what this is for A, you notice A is 2, positive 2, that's bigger than 0, then this one's going to open up. So yes, it will have x-intercepts. So again, it's always good to think about that because you want to look for x-intercepts that don't exist. So since one opens up, it does have x-intercepts. So we can find our x-intercepts, we can find our y-intercepts. Again, you can find either one. They're both useful. We saw before, though, that it's actually usually easier to find the y-intercept. Let's go ahead and start with the y-intercept. Let's do that one first this time. Now remember, to find the y-intercept, we set x equal to 0. So we replace x with a 0. So we get f of 0. So that gives us 0 squared plus 4 times 0 minus 2. And you'll notice in this form, when you go to plug 0 in, the 0 is going to get rid of all the parts that have x's. So this part that have x's, 0 squared times 2 is still 0. 0 times 4 is 0. And all you're left with is the number at the end. So the c over here, this number at the end, is actually going to be your y-intercept because all the x parts are going to go away when you plug 0 in for x. So that actually makes the y-intercept really easy in this form. The c is your y-intercept. So this c, which is -2, is our y-intercept. Almost don't even have to do any work, right? Because the x parts just go away. You're just left with this part. You're left with the -2, which is your y-intercept. So we know it's going to cross right here. So I told you that the y-intercept is kind of a lot easier to find than the x-intercept. You'll see that especially on this problem. And that is enough to graph it. You can see this curve, what it's going to look like over here. On the other side, remember that we have the symmetry. So that line of symmetry that always goes to the vertex, right? Line of symmetry right here. In this case, it's the line x equals -1. Again, it always matches the x value of your vertex. So the line of symmetry is x equals -1. And so by symmetry, we know that since this one's 1 over, there's got to be a corresponding point right there by symmetry. The same length here as it is there. And that's why we know there's a point over there. So that actually gives us enough. You can draw the graph just with those. I'm going to go ahead and find the x-intercepts as well just for practice. But if you're doing the homework or stuff and you want to find the graph, you just need the vertex and an intercept, and that's enough to graph it. That's plenty. I'm going to go ahead and find the x-intercept. To find the x-intercept, remember we set the y equal to 0, which we can think of f of x as y. This whole thing could be y. So that's basically setting this equation equal to 0. So we get 0 equals 2x squared plus 4x minus 2. So that's what we started with. We just replaced f of x with 0. We want to solve this one. Now, a few different things you could do. You could try factoring. This one, before I do too much, I noticed that all these numbers divide by 2. So something you can do with an equation like this, if you're solving a quadratic, is you can actually sometimes make your life easier if you just divide by number that all the numbers divide by. Instead of having to work with bigger numbers, you can work with smaller numbers. So a trick with these is to look for something that they all divide by and just divide both sides. Here, 2 divided by 2 just gives us 1, so that's just plain x squared, because 1x squared is just 1x squared. 4 divided by 2 gives me 2, so that's 2x. And 2 divided by 2 gives me 1, so I get minus 1. So that's what the equation becomes. Over here, 0 divided by 2, remember, 0 divided by 2, well, 0 divided by anything is still 0. And that's why you can always divide out stuff, when you have something that they all divide by and make it simpler. Now when I look at this, I think about factoring. I say, okay, well, now I don't have to worry about a number in front of the x squared, so I just think about 1 multiplies for -1 and adds for 2. And then I stop and go, wait a second, multiplies for -1, adds for 2, that doesn't work. The only things that multiply for -1 are 1 and -1. That's the only way you can do it. And 1 plus -1 is not going to give me 2, it's going to give me 0. So this one actually won't factor. So what do you do if you get a problem like this and won't factor? That's when you pull out that quadratic formula. Remember the quadratic formula says x equals -b, plus or minus square root b squared 4ac all over 2a. You know that. Okay. So that formula is what we're going to use whenever we can't factor. Again, you can use completing the square if you really like that, but I'm just going to use the formula. I think it's a little more straightforward. Okay, so let's use the formula. So -b, that's just the -2. So -2. And you could use formula with the original equation before we divide by 2. You just get bigger numbers and it makes it harder. So I like to divide the 2 out first because I have smaller numbers. It makes the formula a bit easier to use. Okay, so plus or minus root b squared, so I'm going to get 2 squared. Minus 4 times a, which is 1, right? There's a default 1 there. Times c, which is -1. All over 2 times a, which a is going to be, again, 1. Okay, now it's the big part where we simplify it, right? So still -2, plus or minus. 2 squared is 4. 4 times 1 is 4 times 1 is 4, so that's 4, but a double negative makes that a plus. So inside the square root we get 4 plus 4. Watch the sign here. That's a big mistake people make because they don't watch the sign for that part. Over 2 times 1, which is 2. Okay, now I've got to combine those two parts, so I get negative 2 plus or minus, well, 4 plus 4 is 8, so I get root 8 all over 2. Note, with root 8, we cannot divide 8 in 2, because this one has a root, that one doesn't, but we can simplify root 8. Remember that root 8 breaks into 4 times 2, because you can break it up by multiplication. And we like 4 because you can square root 4. You square root 4 and you get a 2. 2 we can't square root, so we just leave it as square root 2 like that. So this actually becomes x equals negative 2 plus or minus 2 root 2 over 2, because we pulled the 4 out of the 8 and square rooted it. That's how I got a 2 in front. So we're looking at what number can we divide out of 8, which is a perfect square, and 4 is a perfect square, something you could square root. And now the trick is, now because we have a 2 on the outside, now we can divide both parts by 2. You always want to make sure when you have a plus or minus that everything on the top, both parts, get divided by 2. I'm not going to divide the root here because this is all one part. So when I divide the 2 in the front, that's already doing this whole thing. I don't divide both the 2 and the 2, I just do this 2. So I'm going to divide negative 2 by 2, I get negative 1, right? 2 divided by 2 is 1, and negative divided by positive is 1, negative. Leave the plus or minus there. Here, these 2's would cancel, multiply by 2, divide by 2 cancel, and we're just left with the root 2. And those would be your x-intercepts. So all that work to get those x-intercepts, and then they end up being awful square root junk, right? This is not what we want when I'm trying to graph. So you can see why the y-intercept, if I haven't convinced you yet, the y-intercept, which really is just that part right there. This was for this problem down here. That was the y-intercept, just that right there. That's the much easier way to find the intercepts. But again, this is good practice because you should be ready for solving quadratics, something we did this section, for your exam. So this is a great way to practice. Remember that if you can't solve it with factoring, you have to use the formula. And you do need to simplify your formulas where you pull stuff out of the root and simplify. That's something you'll see in these quadratic formulas. So yeah, for my x-intercepts, I get negative 1 plus or minus root 2. Which if you want to see what that is about, you could type in your calculator, do negative 1, plus square root of 2. You can see that's about 0.4, and you can do negative 1 minus square root of 2, and that's about negative 2.4. So that's what this would be. It'd be 0.4 and negative 2.4 would be what that would be. So when I look at the graph, I'm going to have something about 0.4, which would be about here. Something at negative 2.4, which would be about here. And that makes sense. You can see if I drew the line, I would try to kind of cross to that point if I drew my line very well. So this makes sense. So I've got good x-intercepts, 0.4 and negative 2.4. But again, I didn't really need to use the x-intercepts. I could have just used the y-intercept. Last thing before I'm done, let's talk about, I forgot to write down the vertex. We found it right there. I don't know why I put it up here instead of putting it here. So negative 1, negative 4, that's the vertex. The domain and the range, though, is the other thing. Let's talk about domain and range. Again, domain, parabola, always negative 50 to infinity. It's the x values. It reaches left and right forever. No matter how steep it looks, it is still going to the right and going to the left. So the x's are always going to be negative 50 to infinity for parabolas, for this parabola shape. The range, however, this does stop at negative 4. That's the bottom. So the range is going to start at negative 4, bracket, because we actually reach there, and go up to forever. So it's going to go up to infinity. And there we go. We know the domain range. We found the axis symmetry, the line of symmetry. Found the vertex. Found those intercepts. And that's the stuff I want you to be able to do with these parabolas, these quadratic equations. Again, if it's in this non-standard form, you have to use that formula to get the vertex, right? That's the one big difference versus the standard form. You can just look and find the vertex. But the non-standard form, you gotta use that little negative b over 2a. It's my favorite small little tiny formula that makes my life a lot easier when I work with parabolas. Okay, so that's it for today. I'll see you on the next set.